In our last video, we learned about an important group of functions called exponential functions. And in this video, we're going to learn about the inverse of the exponential functions. And we discovered that exponential functions are one-to-one, and we know that all one-to-one functions have inverses. So this time we'll explore the inverse of those functions, and they're called logarithmic functions. As we saw last time, the exponential function has the form f of x equals b to the x for b greater than 0, b shouldn't be 1, and x should belong to the set of real numbers. We've depicted two of them here. One is showing an exponential growth curve, the other one is showing exponential decay. We know growth happens when b is greater than 1, and decay happens when the value of b is between 0 and 1. We also learned to solve some simple equations like this one, where it's possible to take both sides and write them as powers with the same base, because when we can do that, then we can use the fact that the exponential function is a one-to-one function, which implies whenever the outputs are the same, that means the inputs must have been the same. So we use this fact to conclude that this is going to imply this, because if two powers are the same and their bases are the same, then the exponents must be the same. So this was very helpful for these simple types of exponential equations. But if we take an equation even as simple looking as this one, we won't be able to use the same technique, because we can't write 15 as a power of 2. So for that, we're going to need the inverse of the exponential functions, and that's precisely what we refer to as a logarithmic function. So now we'll go ahead and formally define the logarithmic function. We're going to use the same restrictions on the base as we had for the exponential function. The fact that the base needs to be a real number that's greater than 0. It shouldn't be 1, and the x values this time should be positive, whereas for the exponential functions, they were all real numbers. We'll find out why when we look at the graphs. Now, the way we define logarithms is actually using the exponential function, because there's an equivalence here. So we say y equals log base b of x if and only if x equals b to the y. In other words, the entire logarithm becomes just the exponent here of this exponential equation. So these two equations are considered equivalent. So what that means is that they're different ways of saying the same thing, in very much the same way, for example, that you can say the cube root of 8 is 2, or you can say 2 cubed is 8. They're basically expressing the same fact, but in different forms. In fact, we call this left equation the logarithmic form of this equation on the right, and we call this exponential equation on the right the exponential version of this logarithmic equation on the left. So this will be the fact that you want to become very comfortable with as we proceed and use the concept of logarithms. And I will remind you of this on most of the pages that will follow. A couple of notational and similar types of notes. One is that when you see this expression log bx like that, you say logarithm base b of x. For short, you can just say log base b of x. In this expression, x is called the argument of this logarithmic expression. And since x equals b to the y and b is greater than 0, notice we're taking a positive number and raising it to a power. x will never become negative. So that's the main reason why we have this restriction, x is greater than 0. We'll see that again, as I said, when we graph it, it'll make more sense. So x can never actually become negative. That's why we need the restriction, x is greater than 0. And also notice that the restrictions that we have on the base of a logarithmic functions are the same restrictions that we had on the exponential function. Namely that the base should always be positive and it should never be 1. So now we're going to go ahead and look at an actual example with numbers. What you really need to understand about logarithms is that basically a logarithm is the invisible exponent kind of between these two numbers, where you need to raise this number to the power of that invisible exponent to get this higher number. So when you see log base 5 of 25, you're going to ask yourself a question. You're going to say, what power of 5 gives me 25? When you answer that question, you found the log. Remember, a logarithm is just an exponent. So one way of dealing with this is just like that, reasoning it out. Another way is you can go ahead and form a simple equation out of this. You can say log base 5 of 25 equals x, just give it a name, and then go ahead and use this conversion. So you see, when you want to go from this logarithmic form to this exponential form, notice the base of the logarithm, like here being 5, becomes the base of your exponential equation. The entire logarithm, which is x here, becomes the exponent, so to the power of x equals, and this in here is going to be the whole power, so 25. So now all we have to do is to solve this simple exponential equation, and we will know the answer. So 5 to the x, we know that we can solve this by making both sides the power of 5, and we end up with realizing that we have two equal powers and they have the same base, so therefore the exponents must be the same. So we get x equals 2, like that. Now, notice that the reasoning that we had in the beginning yielded the same result. So always be aware of the fact that the logarithm base 5 of 25 is just that exponent that you have to raise 5 to the power of to get 25. And that will always make this very simple for you. Just remember, logs are just exponents. So here's another example. As you start to get a little bit more comfortable with these, you should definitely try some on your own before you continue with the video. All right, so as fractions come in, etc., it might start to get a little bit trickier. So definitely set up the equation like we mentioned. So we have log base 7 of 1 over 49 that we're looking for. We'll just go ahead and call it x. Now we're going to use this relationship to convert this to an exponential equation. Never get attached to the letters. Understand the relationships. That's what's important. Someone should be able to switch all of those letters for you, and you should still be able to set up the right relationship, because it's the relationships that you are learning about. So here, notice if we're going to convert this using this relationship here that we have between the logarithmic and exponential forms of these two equations, we get 7 to the power of x equals 1 over 49. The easiest place to start, of course, is the base, because we know that the base of the logarithmic equation is also the base once you convert that logarithmic equation into its exponential equivalent. And The other thing that's easy to deal with is that you know that the entire log is going to be the exponent. That's why x, which is equal to the entire log, is going to go in the exponent position. That only leaves one other thing, which must be what goes on this side, and that's the argument. All right, so now we have 7 to the power of x. We know we can write 49 as a power of 7, but in order to be able to use this rule that b to the x equals b to the y implies x equals y, we have to have the other 7 on the right side on the top as well. So of course we'll need to utilize help from one of our laws of exponents, which, if you recall, said if you have b, for example, to the power of negative n, that's going to be 1 over b to the n. So using this rule, we can write 7 to the power of 1 over 7 squared as 7 to the negative 2. There were 2 versions of this, if you remember. The other one was 1 over b to the negative n equals b to the n. So you use whichever one is appropriate at the given time. For this case, since we have the positive power in the denominator, we're going to be using this one that we wrote first. But sometimes this one comes in handy. So you have to know both. So we get 7 to the power of negative 2. And now, of course, we can conclude that x must be equal to negative 2. Again, as we discussed when we did these in the previous video, this is not a basic event that's taking place here. We're not canceling the 7s or anything like that. We're using the fact that the exponential function is a one-to-one function, and these are 2 of its outputs. Therefore, the inputs must have been the same. Of course, the exponential function under consideration here would be f of x equals 7 to the x. All right, so here we have another problem to look at. Go ahead and try it for sure before you come back. Okay, so if we go ahead and again just give it a name. Once we do that, then we can go ahead and easily convert it to exponential form. Remember, the base, which is 100, is also going to be the base of the exponential equivalent, and the entire log, so all of that, which is x, is going to be the exponent, and the argument is going to be the whole power, so equals 1. So now we have to ask ourselves, 100 to what power could possibly be 1? And of course, again, as you can see, all this is very closely connected to the laws of exponents that we've already learned. So you need to know that any number to the power of 0 is 1, as long as that number is not 0. 0 to the power of 0 is undefined. So as long as you're not raising 0 to the power of 0, you should be fine. So here again, we can see that x is going to be 0. All right, so that was slightly different from the other ones we've done. So, but you need to know this rule. As long as you know this rule, you should be fine. Now we'd like to get some more practice converting between exponential and logarithmic forms of these equations. So let's take a look at a few problems that help us with that. All right, now we have 4 problems here that we're going to convert to exponential form. Notice they're all in logarithmic form, and now we're going to go ahead and convert them. Again, remember that the easy part about the whole thing is that the base of the logarithmic equation is also going to be the base of the exponential equivalent, and We know that the entire logarithm, which is 6, is going to be the exponent. And when you take care of that power, you're going to get the argument on the other side. So we get 1 million. Let's try that again. All right. So for the next one, as you know, same business. The base remains the base. The entire log, which is equal to -3, is going to be the exponent. And the power is going to be the argument. So it becomes really, really easy after a while if you practice it enough. All right, I hope you've definitely tried these before you've come to join me again. So here, of course, we're going to have 125 to the power of -1/3, which is the entire logarithm, which becomes the exponent. And on the other side, we're going to have the argument. So this one is an example to make sure you're not getting attached to these letters. So you should be able to convert this now, because you know where everything should go. So you know that u is the base, so that's going to be the base of the exponential equation as well. And w, which is the entire log, is going to become the exponent. And of course, the entire power is going to be the argument. And that's how we do these conversions. Okay, so now we're going to go in the other direction. We're going to start with the exponential form of an equation, and we're going to convert it to the logarithmic form of the same equation. So starting here, of course, we know that just like we did in the other direction, the easiest place to start will be with the base, because we know the base of the exponential equation is also going to be the base in the logarithmic form. So log base 2. Now let me put the equal sign, because I know the entire logarithm is going to be the exponent. So the 5 will go on this other side. And we know that the power, the whole power, which is 32, is going to be the argument. All right. Again, I hope you've tried this before you join me. If you haven't, you can pause now and try some. All right, so for the next one, we can see the base is going to be 1/3, because it's the same base as the other equation. We know the entire exponent, the logarithm, is going to be the exponent, so that'll be -4 on the other side. And the entire power will be the logarithm. All right. So for the next one, we have log, the base is 64, and the exponent is -1/3, so that's going to be the entire logarithm. And the power, which is 4, will be the argument. This is a good exercise to make sure you're not getting too attached to these letters, but rather are understanding the relationships. So you should be able to convert this now to logarithmic form. So we have log. Now this time we know the base is going to be L. We know that the entire log will be the exponent, so M will go on the other side. And the entire power is going to be the argument, so N will go in here. All right, so that's some conversions there for you. Make sure you get completely comfortable with these conversions before we proceed. All right, so now we're ready to go ahead and solve some simple logarithmic equations. Basically, they're going to be of this form, and you see how we have 3 letters involved. One of them will be missing, the other 2 will be given, and we'll be solving for the missing variable. As we start solving equations, we have to make sure that these restrictions are not violated. And of course, we're going to be using our conversion quite heavily as well. So here we have an equation for the first time. We're going to convert for the first time in the sense that we're solving. So far, we've just been converting. So we're going to go ahead and to solve these, the easiest thing is to go to a more familiar format, which is the exponential format. So we'll go ahead and write this equation in exponential form. So of course we get 5 to the negative 2 equals x. You could have just as correctly written x equals 5 to the negative 2. Makes no difference which side you put which one on, because these two equations are equivalent. All right, so now we go ahead and simply give the answer in a format that has no negative exponents. So we get 1 over 5 squared. So we get x equals 1 over 25. And that's as simple as these get. So if you want to write it as a solution set, you'll just write the solution set contains 1 over 25. Now, the least amount of checking that you'll want to do for a problem like this is to make sure that these restrictions are not violated. That's the minimum amount of checking you want to do. And especially when x is in the argument position or the base position, that's where the restrictions are. Remember, on this other side, you could get any real number. You could get positive numbers, you could get negative numbers, you could get 0. So the real places where things can go wrong are the base position and the argument position. Now we do notice that one is positive, shouldn't be posing any problem. Or we can do a complete check. We could just say log base 5 of, we're going to plug in 1 over 25 for x, and we're going to check to see if that's equal to negative 2. When we convert that to exponential form, we get 5 to the negative 2, and we want to know if that's equal to 1 over 25. And 5 to the negative 2 is, of course, 1 over 5 squared. We want to know if that's equal to 1 over 25. Finally, we get 1 over 25 equals 1 over 25. So it checks out, and we can move on to another problem. So that's how you do these. All right, so here we have another problem with a fractional base. So we go ahead and convert it to exponential form. Let me go ahead and write the argument by itself on the left side this time, just for variety. And on the right side, we'll get the base to the power of the exponent, which is going to be the whole logarithm, like that. So we get 2x plus 5 equals 1 over 27. And of course, you know that the easiest way to solve an equation like that is to go ahead and clear the fraction by multiplying both sides by the LCD, which is just going to be 27. And don't forget to distribute. So we're going to get 54x plus 5 times 20 is 100, 5 times 7 is 35, so 135 equals, on this side, of course, those cancel out, they just leave us 1. So we get 54x equals 1 minus 135. So x, let's go one more step, 54x equals negative 134. So x is going to be negative 134 over 54. I know at least 2 goes into them, so that should be negative 67 over 27. All right, so sometimes students take a look at that and I go, oh, it's negative, you know, Farzin said no negatives in the argument position, so that's no good. But that's not the problem, you see. As long as 2x plus 5 doesn't become negative, we should be having no problems. So if you want to quickly check that before, to make sure it doesn't become negative before you actually do a full check, you can always do that quickly on a calculator. Let's take a look. All right, so here we'll go ahead and multiply 2 by negative, we're going to plug in negative 67 over 27 for x, and then we're going to go ahead and add 5, and then we'll hit enter. Notice it remained positive, so yeah, barely. I mean, that's very close to 0, but that doesn't matter. As long as it's positive, we're good to go. So again, this was the minimum amount of check you should have done anyway. You want to make sure that this doesn't result in a negative number, because otherwise the argument would become negative, which is not allowable. As you know, x needs to be, well, in this case, when we say x, we're talking about the argument. So you have to always think generally. So that's why we have to check. All right, so if you want to do a full check, of course, you can. You just basically have log base 1/3 of 2 times negative 67 over 27, and you want to know if that's equal to 3. So you want to know if negative 134 over 27. Oops, we forgot a plus 5 here. Let's not forget anything. No child left behind. So we have 2x plus 5, if you recall. Okay, that's better. So plus 5, we want to know if that's equal to 1/3 to the power of 3. So we need to combine these two fractions, so the denominator is 27. So negative 134 plus, now in this other fraction, we have to multiply top and bottom by 27. And we get 5 times 27, which again we know is 135. So that'll go here. I go back to my other color. We want to know if that's equal to 1 over 27. And notice negative 134 plus 135 is 1. So we get 1 over 27 equals 1 over 27. So it passes the check. All right, so if you want to write the solution set, it contains one value, and that's negative 67 over 27. All right, so I know that some textbooks, they like to give you these problems that have all these nice answers, but in real life, that's not usually the way it works out. So I actually prefer giving you problems where the answers will be more like real life. All right, so make sure that you're comfortable with this before we proceed. Again, sometimes you may not have time for a full check. Minimum amount of checking, make sure the argument or the base never become negative. Of course, the base should also not be 1. All right, so here we have another one. We're going to go ahead and convert this to exponential form. So we'll start with the base, which is 25 raised to the power of the whole log, which is going to be the exponent. So u equals, now on the other side we know that we always get the argument, like so. All right, so this is actually more practice like the items we did in the previous set. So we want to go ahead and write both sides as the power of the same base. It looks like 5 is going to work for us, so we'll write the 25 as 5 squared. And of course we know we have the rule that says the nth root of x to the m equals x to the m over n. So we get 5, of course here the exponent is 1 to the power of 1/4. So on the left side we can go ahead and use the power rule to turn that into 2u. We get 5 to the 1/4 on the right side, and of course now we have the same base on both sides. If two powers are equal and their bases are equal, the exponents must be equal, so we get 2u is equal to 1/4. Now be careful with that, because that really is only true when you only deal with positive bases. Otherwise, take a look at this example. -2 to the 4 is the same as 2 to the 4 because they're both 16. But see, this does not imply that -2 is equal to 2. So this implication doesn't exist here. So be very careful to only make that deduction to go from this kind of a scenario to this scenario when you're sure that the bases are positive. All right, so now we're going to go ahead and multiply both sides by 1/2 to go ahead and solve for u, or divide by 2, same thing. Multiplying by 1/2 and dividing by 2 are basically the same operation. All right, so we end up with u is equal to 1/8. Okay, so I'm going to leave some of the checks for you, otherwise this video will never end. And but that's how you do it. In this case, our quick check of restrictions is not going to be really causing any problems, because on this side, remember, you can have log can have any output. The range of the logarithmic function is all real numbers, so there's no problem on this side. We always want to make sure we check these two values. These two positions are problems can occur, where problems can occur. On this side, you can have any kind of output is allowable by a logarithmic equation. All right, so make sure you can handle that, and then we'll proceed. All right, as we look back at some of the examples we just did, notice like in this one, the unknown is in the argument position. In the next one that we did, it was also in the argument position. In this one, it was in the exponent position, or the entire log position, so it was on this side. For our next problem, we're going to solve this logarithmic equation, noticing the fact that this time the unknown is in the base position, and we know that the base of a logarithm has to be positive but not equal to 1. So we're going to, so don't be confused with the fact that the x here is not playing the role of what the x is playing in our general definition. You have to be very flexible with that kind of change in mathematics. All right, so do keep in mind x is playing the role of b. So we know that the restrictions on the value of x are the fact that x should be greater than 0 and x should not be equal to 1. So with that in mind, we proceed with solving. So now we're going to use this definition of logarithms to convert this logarithmic equation to its exponential equivalent form, and we end up with x to the power of 3 equals 24. Now, we do know how to handle these based on previous work, and we know that to get x, if we know x cubed, we have to, of course, take the cube root of both sides, and that's what we will do at this point. And we end up with cube root of x cubed equals cube root of 24. Now, on the left side, we know that the nth root of x to the n equals x, as long as x is positive, right? Now, if we don't know that x is positive, right, which we do know in this case, but if we didn't, we would have to be much more precise with that definition. We would want to say the nth root of x to the n equals x if n is odd, and absolute value of x if n is even. But given that x is positive, we don't need to worry about this more complex definition for the nth root of x to the n, and we can just use the simple version which says the nth root of x to the n equals x. Of course, even if we were to use this and worry about it, we would still be okay because we're dealing with an odd index. So we do notice that we end up with x equals the cube root of 24. So now we check it against the restricted values that we have to worry about, and we notice that this in fact is positive, and it certainly is not 1. So it passes the restriction check. So we can go ahead and accept it as a solution. All we need to do is make sure that we simplify it. Now, if you know how to do that without finding the prime factorization, you can proceed. If not, you can quickly find the prime factorization of 24. The smallest prime that goes into 24 is 2. When we divide, we get 12. Again, 2 gives us 6, 2 gives us 3, and 3 gives us 1. So we notice there is one perfect cube hidden inside 24. We put that in the first radical, the perfect cube radical, and then the next one we put the non-perfect cubes factors of 24. So notice that, so 8 goes in here, and what's left? There's only 3 left, right? So we put 3 in here, so we end up with 2 times the cube root of 3 as the value of x. So that's the simple version of the answer, or the simplified version. So that's what we get when we try to solve this equation for x. Make sure that you can handle that, and then we'll proceed. All right, so our next problem is rather similar, but there will be a minor twist we'll have to deal with. So again, we'll look at the x, and we realize that the unknown is in the base position. So again, it has to be positive but not 1. So the restrictions are that x should be greater than 0 and x should not be 1, right? So we go ahead and proceed by using the definition of logarithms to convert this to exponential form. So we end up with x squared equals 50. So notice that when you apply the square root property to solve this, right, we get x equals plus or minus square root of 50, right? Which is, of course, equal to plus or minus, if we break it up, this time we know 25 is the largest perfect square factor of 50, and that leaves a 2. So we get plus or minus 5 radical 2. So we notice right away that if we split that into 2 separate solutions, x equals 5 radical 2 or x equals negative 5 radical 2, this one right away fails this requirement, right? Because negative number is obviously not greater than 0. So this one we reject. And this one, however, so in other words, this one fails the restriction check because it's not positive. This one is positive and it's not equal to 1. So this one passes the restriction check. So be very careful. If this were just an equation in itself that we were solving, we would have accepted both of those solutions. But because we're solving this equation here, and x is the base of a logarithm, we know that we must reject any negative choices, or 1. So, or even 0, right? So we want the base to be positive and not 1. So there's only one solution. If you want to write it as a solution set, we would only include the 5 radical 2. And that would be it. Okay, so just a little minor twist, but it's important to pay attention to it. So again, make sure you can do this before you proceed. All right, next we want to take a quick look at a few facts that pop right out of the definition of logarithms. One quick fact is that, notice if you take the log base b of any number b, that's just going to be 1. Because remember, when you see log base b of b, what do you ask? You say b to what power? There's an invisible exponent there that gives you this, right? And that's going to be the answer for the log. So b to what power gives you b? Of course, that's going to be 1. So why is this true? Because b to the power of 1 equals b. Just take this and put it in logarithmic form, and you'll see that you end up exactly with this equation here. All right, so for example, if you see log base 7 of 7, that's a no-brainer. You know the answer is going to be just 1, right? It's just common sense anyway. If you understand the definition of logs, this is almost not worth mentioning, but these come in kind of often and make appearances, so it's good to be very comfortable with them. Or for example, if you get log base x of x, same business. Could be variable, it could be constant, any way you want it. All right, so the second fact is that if you take the log any base, the base doesn't matter as long as it's a legal base, of course, of 1, you're always going to get 0. Why is that true? Because look, b to the power of 0 equals 1 for any b, right? So that's why it's true. So for example, if you see log base 100 of 1, there's no work needed here. You basically need to know that the number, the exponent, you need to raise 100 to the power of to get 1, which is what's going to go here, which is what the entire log is. Just that exponent is going to be 0. All right, so if we take log base u of 1, it doesn't matter what u is. As long as it's a legal value, you know it's going to be 0 as well. All right, the next fact is very kind of similar to this, but this time we're saying b to what power. Remember, we're looking for that invisible exponent that when we raise the base to the power of, we get the argument. So think about it. B to what power gives b to the x? You answered it, right? Just x. That's it. So for example, and why is this true? Because b to the x, b to the power of x is the same as b to the x, okay? So for example, if you have log base 7 of 49, yeah, it's not in that form yet, but notice I can always write this as log base 7 of 7 squared, which I know now by this rule, which you should not just memorize but fully understand, is 2. So that's an interesting way of dealing with that. Or if you have, say, log base 1/2 of 1/8. You can always write that as log base 1/2 of 1/2 cubed. And now you can see you're in this form, aren't you? 1/2 and 1/2. So you should just get 3. All right. The last one might look a little bit weird at first, but when you think about it, it makes total sense, because we're saying b to the power of log base p of x is x. Well, look, just from a purely substitutional point of view, remember this basic equation that we've been using all video, right? Notice that we say y equals log base p of x on this side, and on that side we have x equals b to the y. So all we've done here is we've taken the y, which is the same as log base p of x, and we've put it instead of the y here. So we end up with b to the power of y, which is log base p of x equals x. So that's just from looking at it and doing a substitution, so it makes sense. However, a deeper understanding tells you b to the power, that you have to raise b to the power to get x, should of course give you what? Give you x. Think about that for a few minutes. See if that makes total sense to you. Because what is log base p of x? It's that power of b, right? That gives what? That gives x. So if you raise b to that power of b that gives x, of course you're going to get x. All right, so for example, if somebody gives you 10 to the power of log base 10 of 50, this is like a gift. There's not a whole lot to do here. Since these two bases are the same, you know the answer is just going to be 50. Or if somebody gives you j to the power of log base j of z, I guess in honor of jz, you just get what? You just get z. All right? So that's a quick summary of these 4 basic facts that pop in from time to time. So you really want to be familiar with them and be comfortable with them, okay, before we proceed. We're almost done. We're just going to look at a couple of graphs and call it the day. All right, so suppose somebody asks you to graph y equals log base 2 of x. Now, you could, of course, make a table of values where you give x values and then find corresponding y values, which means you're going to have to take logarithms. Or you could do what's easier, which is just to find powers. So what we do is we take this equation and we write it in its exponential equivalent, which is going to be x equals b to the y. In this case, x equals 2 to the y. It's the exact equivalent of this equation. So if we graph this equation, we've also graphed that equation. So, but the only catch here is you have to make sure you start by giving y values first. So you're taking care of this column first. You're picking these, then you're plugging these into here to get the corresponding x value. So we're working kind of backwards from the way we're used to working, right? Usually we give x values and then substitute to get y, but now we're doing the opposite. We're giving y values and substituting to get x. So when you substitute -2, you get 2 to the -2, which is, of course, 1 over 2 squared, which is 1/4. Substitute -1, you get 2 to the -1, which is 1 over 2 to the 1, which is 1/2. Substitute 0 for y, you get 2 to the 0, so x is going to be 1. Substitute 1, you get 2 to the 1, which is going to give you 2. 2 will give you 2 squared, which is 4. Plot those, and you get this nice looking graph here. Notice this time, it's not the x-axis like in the case of the exponential function, which is the asymptote. It's the y-axis, and it's not a horizontal asymptote, it's a vertical asymptote. That means a line where the graph comes arbitrarily close to. Remember what that means? That's a technical term. That means it comes, you can get it as close as you want to get it. You can give me any positive distance and say, hey, I want you to bring it within a millionth of an inch. It's doable, right? However, it will never actually cross it. So that's what is meant by an asymptote. So this graph of the logarithmic function has a vertical asymptote. The equation, of course, is just x equals 0 because that's the equation of the y-axis. All right, so let's go ahead and take a look at this and put it next to the graph of the exponential function, see if we notice anything. Okay, so here we're putting the graph of log base 2 of x and 2 to the x on the same Cartesian coordinate plane. We did this in the last video and we did this one in this video. Notice the beautiful relationship between them. They are indeed symmetric with respect to the line y equals x. If you remember from the last video, functions that do that are inverse functions. So they switch domain and range. Notice that the domain of the red graph, which is y equals 2 to the x, is all real numbers, and that's the range of the blue graph. They switch domain and range. The range of the red graph is all positive numbers, real numbers, and that becomes the domain of the blue graph. So they are precisely inverse functions. In fact, we can easily prove it in the case of these two. Remember, if you have two inverse functions and you start with an input, apply one of the functions to get an output, then the inverse should take you back to that. So if you follow those two functions back to back in the form of composition of two functions, start with x, apply f to it, and then apply f inverse to that outcome, you should get back to x. And notice that we do, because f inverse of f of x just means, in this case we're calling the log base 2 of x the f inverse function, so it just means f inverse of log f inverse of 2 to the x. So that means plug in 2 to the x where you see x in this expression. So if I were to add one line here for you in writing, so you have f inverse of f of x is going to be f inverse of, notice what f of x is, it's 2 to the x. So it's going to be f inverse of 2 to the x, which is going to be apply the action of f inverse to this input now. The input is 2 to the x. So you get, instead of x, put 2 to the x. So you get log base 2 of 2 to the x, which is, as we learned a minute ago, x. Or if you go the other way around, you have f of f inverse of x. That means f of, okay, what is f inverse of x? Log base 2 of x. Now apply the action of f. What does f do? You feed f something, it raises 2 to the power of that something. So it's going to do the same with this input. So it's going to take 2 and raise it to the power of log base 2 of x. Recognize this from the previous screen, that's also just x. So here we showed it for the case of base 2, but imagine replacing all these 2's with b. Then you have proven it for all exponential functions and logarithmic functions of base b. So yes, in general, these functions are inverse functions. You can see in their tables too how the outputs here are the inputs here, and the inputs here are the outputs here. You can see the beautiful relationship also in these ordered pairs. Notice how the x and y are switched. That's symmetry with respect to the line y equals x, which is unique to inverse functions. Do notice that when the base is greater than 1, the logarithmic function is an increasing function. Just as with exponential functions, when the base is greater than 1, they're increasing. See, the values of y keep getting larger and larger. Same happens here. Not, of course, as fast as the exponential function in this case, but they are increasing. Now let's see what happens if we look at a base value between 0 and 1. See what happens when you take a base value between 0 and 1. The logarithmic function becomes a decreasing function. And that's exactly what happened with the exponential function as well. All right, and these two, log base 1/2 of x and y equals 1/2 to the x, are obviously also inverse functions. All right, so far in this video we have learned that the logarithmic function has the form f of x equals log base b of x, where the base b has to be positive, it shouldn't be 1, and the argument of logarithm should also be positive. We've also learned that y equals log base b of x is equivalent to the exponential equation x equals b to the y. In the rest of the video, we will learn that the three fundamental rules for exponents that we're familiar with, the product rule, the quotient rule, and the power rule, they're all going to have logarithmic counterparts. After all, remember that logarithms are just exponents. All right, the first property we're going to introduce is going to be the product rule for logarithms, and because it is very empowering to be able to not just know something but really understand it and be able to prove it, we're going to go ahead and prove these rules as we encounter them. So let's go ahead and take a look at how we would maybe prove a rule like this. So we'll go ahead and give these two expressions on the right side here some names. So let's go ahead and let log base b of m be x, and let's let log base b of n be y. We're just giving it any names. You could have called them u and v, your favorite letters, doesn't matter. The game plan is we're going to start with these logarithmic forms. We're going to go to exponential form, take care of some business with the product, and then we'll go back to logarithmic form. So that's where we're headed. All right, so if we go ahead and put both of these in exponential form, we get m equals b to the x and n equals b to the y. That's just a quick application of what the definition of logarithms tells us. Now, since I'm going to be proving something about the log of a product, it's good for me to know what that product looks like. So now we're going to go ahead and multiply m and n. So we get m times n equals b to the x times b to the y. Now, if I just go ahead and use the laws of exponents, this screen is acting a little funny. Okay, here we go. So if we go ahead and apply the laws of exponents, we get mn equals b to the, we're going to use the product rule here to give us b to the x plus y. All right, we've pretty much accomplished whatever we wanted to accomplish using the exponential form. Now we're ready to go ahead and go back to logarithmic form. So we're going to take this equation and we're going to put it in logarithmic form. So we end up with, this implies log base b of Remember, you put the entire exponent on this side because that's going to be the logarithm, and the power, which is mn, will become the argument here. Now we can use parentheses so that there's no confusion. And now all we're going to do is we're going to substitute. You remember what x was? X was log base b of m. And if you recall, y is just log base b of n. And that's exactly what we were trying to prove. We were trying to prove that log base b of mn equals log base b of m plus log base b of n. So it's a very nice simple proof, but it's very indicative of how we approach proofs in mathematics. So make sure that you understand it before we move on to prove the quotient rule. We're going to use exactly the same approach for the quotient rule, which basically says the log of a quotient is the difference of the logs. If we go back to our previous screen, the mnemonic for this, the way you want to remember this, is that the log of a product is the sum of the logs. Okay, so be very careful. Log of m times n is not log of m times log of n. It's the log of m plus log of n. Of course, similar to the rule we had with the exponents too. When you multiply two powers with the same base, you kept the base and you added the exponents, remember? And of course, logs are exponents too, so it's not surprising that they behave in a similar fashion. All right, so we'll use the same game plan. We'll go ahead and give these two items on the right a name. So let's go ahead and let log base b of m be x again, and log base b of n be y. So we'll go ahead and put both of those in exponential form. So we get, this implies m equals b to the x and n equals b to the y. So now this time we're interested in the log of a quotient, so we want to know what the quotient m over n looks like. So this time we'll go ahead and see what m over n becomes. Well, of course, that's going to become b to the x over b to the y. Now if we apply the quotient rule to that, we get m over n equals b to the x minus y. And basically our use of the exponential form has been exhausted, so we go ahead and put this back into logarithmic form now. So we get log base b of m over n equals x minus y. Now if we substitute log base b of m for x and log base b of n for y, we end up with log base b of m minus log base b of n. And we have just proven what we wanted to prove. So QED. All right, so two nice proofs. Make sure you actually can carry them on your own. That's fantastic experience with math and with logic. And then we'll go and prove the power rule, which is the last one that we're going to look at. So the power rule states that if you have the log of a power, it's going to be the exponent times the log. Now this power rule is going to be a particularly important rule for us. They're all three are important, but this is extremely unique because we've never seen any rule until now that takes an exponent and makes it something other than an exponent, in this case a factor. So This rule is going to be extremely powerful and extremely helpful for us when it comes to solving very difficult exponential equations that cannot be solved in the method that we've been using by making both sides powers with the same base. Those are going to require the utilization of this rule in particular. So the proof runs similar. It's in some ways simpler because there's only one log we're dealing with. So we're going to go ahead and do the same thing. We're going to let log base b of m be x. You should definitely see if you can carry this proof on your own, because that would be a fantastic way of gaining some confidence if you can manage that, because I think you'll be able to do it if you understood the previous two proofs. All right, so now we go ahead and write this in exponential form. So we get m equals b to the x. Notice this time we want to know what m to the n is. So we're going to go ahead and raise both sides to the power of n, and we get this like so. So if I just simplify the right side, I get m to the n equals b to the xn, or I'm going to write nx, you'll see in a minute why. So now let's go ahead and take this equation and put it in logarithmic form. So we get log base b of m to the n equals nx. Now all you have to do is remember what x is. Remember, log base b of m. So we get n times log base b of m. Isn't that what we were trying to prove? That the log of a power is the exponent times the log. And that's exactly what we accomplished. So notice how the game plan was the same for all of them. We start with logarithmic form, go to a simpler form we're familiar with and we know the rules of, do what we need to do, and then get back to logarithmic form to end the proof. And that's basically all three rules that we're going to be using. We'll look at a summary in a second. Okay, so here we see a summary of the rules that we just proved. The product rule, which of course told us the log of a product is the sum of the logs. The quotient rule, which states that the log of a quotient is the difference of the logs. And the power rule that tells us the log of a power is going to be the exponent times the log. These are extremely important rules. Just like with the laws of exponents, we're going to be using them extensively in the next few sets. So make sure you have these completely down. Now let's go ahead and apply the properties we just proved to a few actual examples. All right, here on the left we have the log of this product. We're going to be applying the product rule a few times first to get comfortable with that one. And remember, the log of a product is the sum of the two logs, the two basically logs of the two factors. So here we're going to go ahead and break this down as log base 10 of 2 plus log base 10 of 100. Now log base 10 of 2 is not a simple number because we don't know what power of 10 gives us 2, but log base 10 of 100 is a nice simple number. Remember that invisible number you have to imagine here. 10 to what power gives 100? That's 2. So we go ahead and say that's equal to log base 10 of 2. We don't do anything with that one. But the next one we can just simply write as 2 because that's what log base 10 of 100 is. It's 2. All right, this next one we can go ahead and split that up as log base 7 of 49 plus log base 7 of x. Now log base 7 of 49 we know is 2. What power of 7 gives us 49? The second power, and plus that one, the next one we just write and leave as is. The next one, we're going to apply the product rule twice. So the first time we can, for example, apply it to u and then vw, and then we apply it again. So we end up with log base b of u plus log base b of u vw. So we split it up kind of like this right now, and now we notice we can apply the rule again to this log of a product. So we end up with log base b of u plus log base b of v plus log base b of w. Now normally we don't show this step. We understand this, and then from this point forward, when we see that, we know that that's just going to be the sum of each log, the log of each factor anyway. So normally we jump from this to this outcome and we bypass that step. Okay? All right, so let's move on to a few more examples. Remember that in mathematics, whenever you learn a formula or any kind of a equation, you have to be comfortable with it from the going from left to the right and backwards from right to left. So now we're going to go in this direction from right to left. We're given a sum, and we're going to write it as the log of a product. So, and if we can, we'll simplify thereafter if possible. So here we notice that we can write this as log base 10 of 2 times 50, which is log base 10 of 100, which of course does become a nice simple 2. What power of 10 is 100? We know that's just 2. So that's the final answer there. So for the next one, we're going to take that and we're going to write it as log base 5 of basically just the product, like that. And that's all we can do there. So sometimes people use parentheses on something like that, and sometimes they don't. We'll go ahead and use it. It's a little bit safer. All right. So here, of course, this 7 is going to play the role of m, and this entire factor, not part of it, but the entire factor is going to play the role of n. So we're going to get log base 2 of 7 times x minus 3. Now the only other thing we can do is just go ahead and distribute that. Here you must use parentheses. So we get 7x minus 21. The reason for the must is because if you write log base 2 of 7x minus 21 without parentheses, others will assume that you have to take this log and then subtract 21, which is not what you want to be interpreted as. So make sure that you use parentheses on that one. Okay, let's go ahead and apply the quotient rule a few times. So we know that the log of a quotient is the difference of the logs. So for this first one, we're going to get log base 10 of 79 minus log base 10 of 100. So log base 10 of 79 is not a nice simple answer. We just leave it as is. But this one we know is 2. Like so. The next one, we're just going to get log base 4 of m minus log base 4 of n, and there's nothing else we can do. For the next one, we're going to get log base b of 1 minus log base b of b. both of those should look familiar to you. What power of any positive number is 1? You guessed it, 0. And minus what power of a number is itself? You guessed that too, 1. So the final answer will actually be -1, like so. All right. So make sure you're comfortable with these, and then we'll proceed. All right, as we did with the product rule, we're going to now go from the right to left direction. So we're given a difference of 2 logs, and we're going to write it as a log of a quotient. So here we're going to get log base 10 of 3,000 over 3. We know that that's log base 10 of 1,000, and I think you'll be able to answer that, right? What is log base 10 of 1,000? What power of 10 gives us 1,000? In other words, what exponent do we need? You said it. Oops, here we go again with this business. All right, I managed to tame the wild whiteboard again. All right, so we know that 10 to the power of course, 3 is 1,000. So the answer is 3, and that's all it is. All right, for the next one, we're just going to get log base 5 of x over y. This is just to give us some practice with the rule. Here, of course, 7x is playing the role of m. The entire expression y minus z squared is playing the role of n. So we're going to get log base 2 of 7x over y minus z squared. Now let's go ahead and take a look at a few problems involving the power rule, which of course states that the log of a power is the exponent times the log. Remember, it's an extremely important rule because it's the only rule we have in mathematics that takes an exponent and turns it into a factor, thereby releasing it from its imprisonment in that exponent position. All right, so if we go ahead and take a look at these, we're going from basically from left to right. We have the log of a power, and we're going to turn it into this product here. So the first one is going to become 4 times the log base 3 of 5, and there's not much else we can do because log base 3 of 5 is not a very basic simple number. All right, for the next one we have log base 8, and you may wonder why that's even here, because of course, as you know, we can write a radical as a fractional power. So we can go ahead and write that as 64 to the power of 1/3, and this in turn we can simplify using the power rule, because now we know that we can bring the 1/3 over here and turn it into a factor. So we get 1/3 times log base 8 of 64. Now we know what log base 8 of 64 is, because we know 8 to the power of 2 gives 64. So log base 8 of 64 is 2. So times 2, so the final answer we'll write as 2/3. Now here we're going to go ahead and just bring the 6 down, and we get log base b of quantity, parentheses are mandatory here, just like that, and we're done. There's nothing else we can do. Remember, we never did a log of a sum rule, did we? And that's because it doesn't exist. So don't do anything after that. You are finished. This is not log base b of m plus log base b of n. Okay, so make sure you don't make that mistake. Just leave it as is. All right, as is common to what we have been doing, now we're going to go from right to left. So we're given some products, we're going to write those as powers, log of powers. So this becomes log base 2 of 7 squared. So we just basically get log base 2 of 49. And that's all we can do there. The next one, we're going to get log base 5 of x to the negative 3, which we can of course write as log base 5 of 1 over x cubed, like so. On the next one, we're going to write log base b of u to the 1/4. If a problem demands it, you can of course always write that as log base b of the 4th root of u, and that would be correct as well. All right, so there's some practice with these rules. Now, if you recall, these two rules we also looked at in our previous video. You know that log base p of b to the x is x, and b to the power of log base p of x is also x. So if we apply these, we end up with, for example, in this one, notice the role of b is being played by 10. Since the base here and the base of that power are the same, we're just going to get 20. On this one, we have to do a little bit of work first. So we have to take the 8th root of 5 and first write it as 5 to the power of 1/8. Now we can see we're exactly in this format, and we're going to just get 1/8. Here we have 9 to the power of log base 9 of CD. We're in this format. As long as this base here and that base are the same, we're just going to get the argument. So we're just going to get CD. That's all. Same here in this next one. As long as these two are the same, the base here and the base of the log, we're just going to get whatever that argument is. So here we're just going to get square root of x. All right, so the last thing we're going to do now is to combine all these logs in the same problem. So first we'll just review them. Remember, these are all the rules of logs we've studied so far. We started with just the basic definition of logarithms, which you should be familiar with by now. Then we did the product rule, the quotient rule, the power rule, the log of 1 rule, the log base p of b rule, the log base p of b to the x rule, and the b to the log base p of x rule. So these are the inverse rules basically, and we're going to be utilizing some or all of these in the next few examples. All right, in this example, we want to write this log as a combination of single logarithms. So what do we mean by simple logarithms? We mean logarithms of where the argument is just either a constant to the power of 1 or a variable to the power of 1. That's what we mean by simple logs. You'll see in a minute what they look like. So the first thing we'll do, well, let me just go ahead and copy the problem down. So let's go ahead and first and foremost apply the product rule. So we get log base 5 of 5 plus log base 5 of x to the 5. Now, so here the property we used was the product rule. And of course, we used it from left to right. Now we can go ahead and remember this basic rule, the log of base b of b equals 1. And log base 5 of x to the 5, what we can do is we can bring the 5 down. So we get 5 times log base 5 of x. Now, notice that is a simple argument because it's just a variable to the power of 1. And there's really not much else we can do. So here at this point, we are done. And the property we used here was the power rule, also used from left to right. And that will be the final answer of the rewriting of that expression. Okay, so next we're going to take a look at this problem, and the first thing we'll go ahead and do is turn that radical into a power in this way. So we can say log base 8 of 8 over y to the power of 1/2. And here, of course, we're just using the radical to fractional exponent rule. And if you recall, that says the nth root of x to the m equals x to the m over n. And now we're going to go ahead and apply the power rule for logarithms, and this will give us 1/2 log base 8 of 8 over y. So the property used is the power rule, which of course says log base b of x to the n equals n times log base b of x. Next, we'll go ahead and apply the quotient rule, which says log base b of m over n equals log base b of m minus log base b of n. So here we will get, in parentheses, log base 8 of 8 minus log base 8 of y. We need the parentheses because the 1/2 needs to get distributed into the group. Okay, so make sure that you do use parentheses there, and that gives us, upon distribution, 1/2 log base 8 of 8 minus 1/2 log base 8 of y. Here we're just using the distributive property. And the last thing we want to do is go ahead and remember this rule, that if you have the log base b of b, that equals 1, for obvious reasons, right? Because b to what power gives you b? That would have to be 1. So we can replace log base 8 of 8 with just 1. So we get 1/2 times 1. This becomes 1. So that's just 1/2 minus 1/2 log base 8 of y. So there is the expanded version of this particular expression, written as a combination of simple logarithms, meaning logarithms with nothing other than just a simple variable, no powers or anything on it. All right, so make sure you can handle that, and then we'll proceed. All right, so here, obviously, if you look at it, the top level operation we're going to deal with here is a quotient. So we'll go ahead and use the quotient rule to write that as log base b of PQ minus log base b of RS. And of course, we're using the fact that log base b of m over n equals log base b of m minus log base b of n. So now we notice that we have two products that we can deal with. So we have a log of a product here and a log of a product here. So the first one gives me the sum of the logs. So log base b of p plus log base b of q minus, I am going to need parentheses here. So the first thing that we did was we applied the quotient rule. And now we're applying the product rule. So we get minus log base b of r plus log base b of s, all within parentheses. Finally, we're just going to go ahead and distribute that negative. So we get minus log base b of r. Be careful where you locate that. It should be at the same level as the log, minus log, and we always want the base on there. So minus log base b of s. And that should do it. That's all we can do. Notice each of these logs is a simple log because their power is 1, just a variable or a constant to the power of 1. So here we just did some simplifying. So that's all there is to it. Okay, let's look at another one. All right. Of course, you know how when we go from this side to that side, now we're going to go the other way around. We always do that in math. So now we're going to take this combination of logs and turn it into a single logarithm. We're doing the exact opposite of what we just did in those few examples. So we'll start with 4 log base b of a minus 5 log base b of b. So obviously, if I'm going to try to get these into just one logarithm as a format, first I should go ahead and get rid of the 4 and the 5 and take them and make them powers using the power rule. So I get log base b of a to the 4 minus log base b of b to the 5. Notice since I kept the minus here, it doesn't go onto the exponent. If I wanted to do that, I would have written plus and then I would have put the minus there, but we don't need to do that. All right, so here we just applied the power rule, of course, going that way. And now we can go ahead and write that as the log of a quotient, because remember, a log of a quotient is the difference of the logs. So we get log base b of a to the 4 over b to the 5. And here we apply the quotient rule, of course, going in that direction once again. All right, so that's how you tame those beasts. All right, let's look at another. All right, so here again we have a combination of logarithmic expressions, and we're going to go ahead and combine them into just one log. So we'll go ahead and start by applying the power rule again. So we get the log base b of x to the 1/2 minus log base b of y to the 1/3. And here we just applied the power rule, so let's keep track of it. And now we're going to go ahead and apply the quotient rule since it's a difference. So we're going to get log base b of x to the 1/2 over y to the 1/3. There we just use the quotient rule. And finally, if we like, we could just go ahead and write those as radicals. So we can say log base b of square root of x over the cube root of y. There we're just using the nth root of x to the m equals x to the m over n rule. And that's all there is to that one. All right, here we're doing a couple of true or false questions we may encounter. So to handle a question like this, just go ahead and figure out what the left side is. Go ahead and figure out what the right side is. See if they're the same thing. So let's start with the left side. We have log base 3 of 27 over log base 3 of 9. So we know what log base 3 of 27 is. 3 to what power is 27? You said it, 3. And we know what log base 3 of 9 is. 3 to what power is 9? And the answer is 2. So that's what we have for the left-hand side. So if you want, you could put it like this. Then you can say the right-hand side is equal to log base 3 of 27 over 9. If we go ahead and divide 27 by 9, we get log base 3 of 3, which is, we know what is the power of 3 that gives 3? 1. So you notice they're not the same thing. So this is actually a false statement. And this is in order to, this is basically considered a counter example for this rule. So suppose somebody comes to you and says, hey, I just learned about logarithms. Did you know that the log base b of m over the log base b of n is equal to log base b of m over n? So instead of arguing with the person, all you have to do is show them this one example, and that proves that this statement is not true. So this really requires one of those lines through it because they're not the same thing. So in order to prove a mathematical statement true, you have to do some work like we did in the beginning of the video, proving the 3 rules of logarithms. But in order to prove something is not true, or that it's false or wrong, not a theorem or a true statement, all you have to do is show one example. So to prove that this is not a law of logarithms, we don't have to like sit here and write a full page of proof. No, all we need is one example, because the standard of truth in mathematics is extremely high. If you say something works, it has to work every single time. If it fails even once, we don't accept it as a rule. Let's look at the one on the right side now. So we'll start with the left-hand side, which is log base 2 of log base 3 of 9. Using the order of operations, we'll start from the inside. So we need to figure out log base 3 of 9. Of course, we know that's just 2. So this becomes log base 2 of 2, and we know that is just 1. So that's what the left-hand side gives us. The right-hand side is log base 11 of 121 over log base 12 of 144. Now we know log base 11 of 121 is just 2 because 11 squared is 121. And we know that log base 12 of 144 is also 2 because 12 squared is also 144. So this becomes 1. So here we can say this statement is true because the left and the right hand side are indeed the same. All right, that was the last example we were going to look at. So I just wanted to close the video by warning you about these common errors, okay? Log of a product is not the product of the two logs. Log of a quotient is not the quotient of the two logs. The log of a power doesn't mean take the log and then raise it to the power. As you know, what it is you have to bring the exponent down and multiply it. The log of a sum is not the sum of the logs, and the log of a difference is not the difference of the logs. There are so many things that you can't do with logs. The best thing to do is just to learn the few things you can do and then learn them well and apply them appropriately. All right, so I hope that helps out, and practice plentifully as always, and I'll see you in the next video. Be safe.